Hello AP Stat students, this is Mr. Hazelhorst and the first of two presentations on the binomial distribution. A couple of reminders here as we get started. First off, I want to encourage you to pause and rewind the video as you need to. That's the nice thing about working in a flipped classroom is you don't have to go at my pace, you get to go at your pace. So if you need to rewatch something, feel free to rewind. If you need to pause so that you can take notes, feel free to do that as well. And that's my second point, make sure you take notes. Remember, you get to use your notes on quizzes. So this is where your notes are going to come from, all right? So it's to your benefit to make sure you watch this distribution. Feel free to print the notes off from my class website and just write on top of those, or just take notes like you would in a regular classroom. But I do highly encourage you to take notes. Finally, once you finish watching the video, on my class website below this video, you'll find a Google form, and I just ask that you fill that in and complete that. That's kind of my record keeping to know that you watched the video. Now, that will also give you the opportunity to comment on any questions that you may have even after watching this video. So when you get done, if there's still something that's not very clear to you or that you don't completely understand, make note of that in the comment section. I'll read all of those and then use those to help guide our discussion to start class as we discuss the binomial distribution in a couple of days. So let's jump right into it. If you have your graphing calculator with you, go ahead and pull that out. We will use that today because the good news is, like a lot of the things that we do in this class, the binomial distribution is built into your graphing calculator. But we'll get to that here in a little bit. First off, let's talk about the characteristics of a binomial distribution. Now, we have that prefix bi, so one of the characteristics probably is not going to surprise you too much. The first characteristic of a binomial distribution is the fact that there are only two outcomes. Now, there's a lot of random phenomenon that we study and already have studied in this class where there's only two outcomes. Think about how many times we talked about flipping a coin where there's only two outcomes there, heads or tails. A lot of you are probably rooting for a snow day here at some point over the next couple of months. And so whether or not we have a snow day is a binomial or only has two outcomes. You either have a snow day or you don't. When we think about the multiple choice questions on your test, those only have two outcomes. Now, we might have multiple choices to make, but ultimately it boils down to, was the question correct or incorrect? So there's only two outcomes there, all right? The second characteristic is that there's a fixed number of trials, and that fixed number of trials we'll label with a variable n. And then the third and final characteristic is that each of the events needs to remain independent. So if I'm going to flip a coin 10 times, we already know that one flip is not going to impact the result of a following flip. All 10 of those flips are independent. Same thing if we were going to study snow days. If we were going to look at a week period and the probability of getting a certain number of snow days over that period, we would need to be able to establish if each of the days are independent from the previous days. Okay? So these are the three characteristics that make up the binomial distribution. Now, it's a notation that you need to be aware of. This is similar to what we saw for notation of the normal distribution back in Chapter 2. So the special binomial notation is that we'll see a capital B and then followed by a set of parentheses. The first number in the parentheses will always represent that fixed number of trials that we talked about in the characteristics up above. And then P will represent the probability of success. And when we say the probability of success, that's whatever we're considering a success in the context of the problem, okay? That's what P will represent. Again, you can see this is very similar to the notation that we use for a normal distribution when we would kind of just abbreviate the normal distribution in terms of its mean and standard deviation. Those are the two key characteristics of a normal distribution. The two key characteristics of a binomial distribution are N and P. So let's take a look at a couple of situations and see if you can identify these as binomial. So first one, question is this binomial? The number of heads when flipping a coin. So feel free to pause it and think about that for a moment. Now, a lot of you may think that, yes, this is binomial. There's only two outcomes, heads or tails. But remember, we have three different characteristics. And the second characteristic is not met in this situation. How many times are you going to flip that coin? We're not specifying that here. So we don't have a fixed number of trials. We don't have one of those key characteristics. We don't have the variable n. So this problem is not binomial. How about this one? The number correct on a 10-question true-false quiz. So if you just go down the list of characteristics, do we have only two outcomes? Answer there, yes. You either get it right or you get it wrong. Now, we don't care if it's true or false. What we care about is it right or is it wrong. So yes, only 2 outcomes. Second, we have a fixed number of trials because there are only 10 questions on this quiz. So it's going to come to an end at some point. And then finally, we can assume that all the questions are independent of each other. So this problem would be considered binomial. We meet all 3 characteristics. So how about this one? The number of red cards when 7 cards are dealt from a deck. Now, when you think about dealing cards, as we know, when it comes down to cards, the question is, are those cards being replaced or not? Well, let's think about both situations. Let's say that the cards are being replaced. So, would we have only 2 outcomes? Yep, they're either red or they're black. Do we have a fixed number of trials? Yes, only 7 cards. Or would they be independent? Well, if we're replacing the cards, the answer to that question would be yes. So if replaced, this would be a binomial setting. If not replaced, this would not be a binomial setting because we know the probability would change from one trial to the next. So we would have independent events in that case. All right. So a couple more here. The number correct on a 10-question multiple choice test. Now, if you learned anything from the beginning parts here, hopefully you answer yes here pretty quickly. Again, you might think, well, there's 4 choices per question, but that's not what we're concerned about. What we're concerned about is the number correct and the number incorrect. So we have only 2 outcomes. We have a fixed number of trials, 10, and they would be independent of each other. All right, last one that popped up, the number of times you roll a die before you roll a 6. And we have only 2 outcomes. Yep, you either roll a 6 or you do not. So there's 2 outcomes there. They'd be independent. We know that on the die. But the question, or the problem we run into, again, on this one, just like the very first bullet point, we don't have a fixed number of trials. We don't know how many times it's going to be rolled. So this would not be considered a binomial setting. So if you can identify a problem fits the binomial distribution, then we're allowed to use the binomial distribution formula. And here's that formula. Now, this formula is found in your gold packet. So you don't necessarily need to write this down in your notes, but you do need to know how to use it. And again, remember, I'm going to show you how to do this on your graphing calculator as well. All right? So this formula is really just an extension of the multiplication rule. All right? If we're interested in observing some random phenomenon n number of times, and there's only 2 outcomes, and the probability of success is p, right? Well, then we're either going to have a bunch of successes and a bunch of failures, and they're going to be mixed up in different orders. And so this part of the formula that we see here is really just the multiplication rule. How many successes do you have? How many failures do you have? All right? Now, does it really matter what order those come into? And the answer there would be no. And so what we also have to take into consideration is this lead coefficient that we refer to as the binomial coefficient. And this is also known as a combination. All right, you've studied combinations in other classes, so we're not going to go into a lot of detail there. But we know that ultimately in a combination, order does not matter. And the same is true in a binomial setting. If we're interested in how many, or the probability that you get 7 questions correct on a 10-question multiple choice quiz, we don't really care what 7 you get correct, just that you get 7 correct. And so that's where the combination part comes into play, and that's a very important part of this binomial probability formula. Now, this phrase binomial coefficient, that'd be a good thing to be aware of. That's going to pop up at times, whether it's in class or even on questions on your test. So keep that in mind. All right, when we talk about the binomial coefficient, it's just the combination. How many different ways or how many combinations are there towards, again, the number of successes and failures that we can make. So this is the formula that we're going to use, but again, it's built into your graphing calculator. So let's take a look at that. Right, in your graphing calculator, it's pretty easy to get to the binomial distribution. We've used other distribution values, and so the binomial distribution is found in the same place. If I use my calculator, turn it on here, hit second, and then the vars button, we know that accesses our distribution menu. So we've used the normal distribution, and we will use a lot of other distributions down the road. But what we're going to use in this problem are what are known as the binomial PDF and the binomial CDF. Now, if you take a look over here, they both require the same input values. The number of trials, the probability of success, and then this value K, which is we're going to refer to as the number of successes. How many successes are we looking for in this given problem? Okay, so that'll change from one problem to the next, but that's what K will represent. Now, we also have to understand the difference between a PDF and a CDF. In a binomial PDF, This is, PDF stands for probability distribution function. This is used to find the probability of a single event. What you can think of here is the word exact. What's the probability that you get exactly 7 correct? Whether you flip exactly 8 heads when you flip a coin 10 times. All right? That's a single event. The CDF, which stands for cumulative distribution function, is used to find the probability of at most situations. All right, so if you think about that, if I say, what's the probability that you get at most 7 questions correct on a quiz? Well, if I say at most 7, that could mean that you got 7 correct, or 6, or 5, or 4, or 3, or 2, or 1. So it's taking all of those situations together and it's cumulating them. That's why we call it the cumulative distribution function. So if you choose the CDF on your graphing calculator, when you plug in that K value, it's also going to find the probability of all the whole numbers down to 0 and then add those all together. So it saves us a lot of work. All right? So let's take a look at a couple of example problems and let's see how this graphing calculator works. This is the main part of this video, is understanding just how to set up the binomial PDF or CDF for different problems. So let's take a look at an example problem here. Right? So it says among high school seniors, 25% have never had a job. Select 10 high school seniors at random. So the first question we have to answer is, does this situation follow binomial distribution? So if we think of the 3 characteristics, do we have only 2 outcomes? Well, the answer there would be yes. You've either had a job or you haven't. Or do we have a fixed number of trials? The answer there would also be yes. We're going to select 10 high school seniors at random. And then finally, would all of these be independent? Well, I think it would be safe for us to assume whether or not I've had a job, right, isn't going to necessarily affect somebody else. So we're going to assume independence in this case. All right, so this situation would follow binomial distribution, so we need to identify what N and P are for this problem. All right, well, remember, N is representing your number of trials. So N will be 10 in this problem. And our P value is representing the probability of success. So what's the probability that somebody has never had a job? Now, in this problem, we are considering never having a job a success, which some of you might consider very successful. That at some point, you're probably going to need a job. So when we use the word success, it's just in the context of the problem. Keep that in mind. All right. So our probability of success is 25%. So 0.25 will represent that as a decimal. Okay? So now, we have some sub-questions here. So the first one is, what is the probability that exactly 2 of the 10 seniors in your sample have never had a job? All right? Now again, notice the word here is exactly. So are we going to use a PDF or are we going to use a CDF in this situation? Well, hopefully you recognize, okay, this is exact. Right? This is only one specific outcome. So this would be one of those PDF problems. So if we set up our command in our graphing calculator, and I want you to get in the habit of writing your work out this way, just like you're going to see us do in this video here through this problem. So we go binomial, and then we're choosing the PDF, and we're just going to write out the command. So again, remember, whether it's a PDF or a CDF, it always follows the same 3 values. First off, we need our number of trials, which is 10. Then we need our probability of success, which is 0.25. And then finally, we just plug in our K value. Right? So what are we being asked about specifically in this problem? Well, we are being asked the probability that exactly 2 of the 10 seniors have never had a job. So that's our K value, 2. So if we pull up our graphing calculator, let's see what this probability comes out to be. So we're going to choose the binomial PDF. We're going to input our command here, so 10, 0.25, and 2. So our probability here comes out to be approximately 28%. Okay? Let's move on to letter C. What is the probability that 2 or fewer have never had a job? So again, the first thing we have to determine, are we going to use a PDF or a CDF in this situation? Right? Well, the first question said exactly 2. This time it says 2 or fewer. So if we think about that, 2 or fewer could be 2, 1, or 0. Well, this is where the CDF comes into play. This is the same as saying at most 2. So in this problem, we're going to use the binomial CDF. Our number of trials is still 10. Our probability of success is still 0.25. And the k value doesn't change at all either. We're still looking at 2 or fewer. So the k value is still 2. Now the difference between this problem and the problem that we had up above is, again, up above was exactly 2. Well, now we're going to take the probability of 2 never having a job, 1 never having a job, and none of them never having a job, and it's going to add those together. So again, if we go back to our graphing calculators here, go back to the distribution menu. This time we're going to choose the binomial CDF. Same command here, 10, comma, 0.25, comma, 2, and we hit enter. And we can see a probability here of approximately 53%. So we would expect to be higher since it accumulated 3 different situations, 3 different probabilities and added them together. All right? So let's move on to letter D. What is the probability that at least 4 have never had a job? So if I look at this kind of the phrase saying at least 4, so that means it could be 4, 5, 6, 7, 8, 9, or 10. All right, now you might think, well, I'm going to use a CDF here, right? But remember, our CDF was set up for at most situations. This is asking at least. So how do we do that? Well, PDF's not going to work, all right? CDF's not going to work, all right? But if I think about at least and at most, those phrases are really complements of each other. So I actually can use the CDF. I have to use it in the context of a complement, however, right? So if I'm saying at least 4, well, that's the complement of at most 3. So I'm going to use the binomial CDF and then subtract that from 1. So here's what our work's going to look like. We're going to go 1 minus the binomial CDF, 10.25, and then again our k value in this problem would be 3. At least 4, again, is the complement of at most 3. So that's the work that we're finding. All right, we're going to find the complement of at most 3. And we can type this into our graphing calculator as well. So we'll go 1 minus, in the distribution menu, we'll choose the binomial CDF. So 10.25 and 3. And there's our probability, right at approximately 22%. Okay? So again, this is the big part that we want you to take from this video, is this ability to identify whether it's a PDF or a CDF and set that up correctly. And this is what we work on here in the next few days in class. All right, so as we come to the end of our first video, I just want to remind you to make sure you complete the form below the video on my class website. And this is just one of 2 videos over section 8.1. So you also need to watch the second video that's listed below, that's titled The Normal Approximation of the Binomial Distribution. And if you're watching that right away next, I'll see you soon.